JK flip-flop. We have seen SR flip-flop. There is problem with SR flip-flop. When you apply both inputs S and R1, the output of SR flip-flop becomes indeterminate. That condition is called race around condition. But in many applications, we need to apply both of these inputs to B1. That is why we should have some solution for that condition. There is a JK flip-flop in which the race around condition is removed. You can see the circuit diagram shown. We have two NAND gates at the input side and two NAND gates at the output side. Now the first two NAND gates, which are at the input side, has got three inputs. Out of them, one is clock, second one is input, and third one is feedback. Okay, then we have this truth table. The truth table is very easy. It is similar to SR flip-flop. There is only one change, and that is this row. In this row, if J and K both are 1, then if Qn is 0, it becomes 1, and if Qn is 1, it becomes 0. That is called toggle. Toggle means to change. If previous output was 0, it will become 1. If previous output was 1, it will become 0. Rest of the truth table is similar to SR flip-flop. For J and K 0 0, if Qn is 0, it will remain 0. For J and K 0 0, if Qn is 1, Qn plus 1 will remain 1. So that is called hold, continue. So whatever was Qn, it will be carried forward. For J and K 0 1, it will clear the flip-flop. It means if Qn is 0, it will make it 0, or it will keep it as it is. If Qn is 1, then it will be made 0. So in case of a reset condition, if previous input was 0, it remains 0. If previous output is 0, it remains 0. If previous output is 1, it will become 0. So somehow it will see to it that output is always 0. Then in the third row we have J and K 1 0. Here it will set the flip-flop. It will set the flip-flop means it will see to it that output becomes 1. Output becomes 1. If its previous output was 0, it will make it 1. If previous output was 1, it will keep it as it is. So this is how your JK flip-flop works. And then we have T flip-flop. In T flip-flop, we have this circuit diagram. Okay, there is only one input labeled T, and this T input is shorted to both of the NAND gates. This is your truth table. Truth table is very simple. T stands for toggle. If previous output was 0, then it will remain 0 if T is 0. If previous output was 0, it will become 1 if T is 1. Right? So somehow it sees to it that output toggles, but for condition for toggling is that T has to be 1. Okay, then only it will toggle. If T is 0, it will not toggle. So you can look at this particular truth table once again. Wherever you find T0, there is no change in Qn and Qn plus 1. They are same. Okay, and wherever you see the T be 1, so the Qn will change. If it was 0, it will become 1. If it was 1, it will become 0. This is how your toggle flip-flop works. This toggle flip-flop is very, very important. It's used in many other applications like ring counters and some other applications also. So you have to remember the circuit diagram, its truth table, and explanation.